now move to the second talk of this morning session. And this talk is by Dootika Vats. She's a faculty member at IIT Kanpur. And she will be talking about efficient Bernoulli factory MCMC for intractable posteriors. Dootika?
Thank you, Shrikar. And thank you so much to the organizers for the invitation. It's a shame I couldn't be there in person. We have final exam week going on here, but it's nice to be online as well. Right, so I'll be talking about MCMC, which stands for Markov Chain Monte Carlo, particularly for intractable posteriors. And I'll explain a little bit about the intractable posteriors part. I'll explain a little bit about the MCMC and a little bit about the Bernoulli factory as well. So this work is joint with Flavio Gonçalves, who's at UPMG in Brazil, and Chris Latrushinsky and Gareth Roberts, who are at the University of Warwick. Okay, so essentially, first I start with the problem of, in general, intractable targets. And when I say targets, I mean a target density or a target distribution, which we, as statisticians, typically are found in Bayesian modeling. So the idea is that we have some data, the y's given a particular parameter theta follow a certain pattern, which is called the likelihood. We may have some prior opinion about a parameter theta, which is encoded in the prior distribution over the parameter space. And having observed the data, we update the information in the prior through an application of the Bayes theorem. And that gives us a posterior distribution, pi theta given y. As is often done in this in Bayesian sort of discussions, I will abuse notation and refer to pi as both the density and the distribution. And the proportionality constant over here is basically the integral over the right-hand side. And the integral with respect to theta of the right-hand side often becomes intractable or unavailable to us. That integral can't be solved. So because pi theta given y has to be a target density, has to be a valid density, we know that it's a unique proportionality constant. So we can just write that this is equal to some pi tilde, where a constant times pi tilde defines a proper density. So the posterior is then typically quite complicated, this posterior distribution, either in a large parameter space or in general takes sort of a complicated structure. This is where MCMC or Markov Chain Monte Carlo algorithms are used to basically draw samples from this distribution using a computer algorithm. And these samples are drawn in such a way that they actually mimic the target distribution. They mimic the properties of the posterior. Okay. And this is typically done, through what are called accept-reject based Markov Chain Monte Carlo methods. So I won't really go into the theory of MCMC, because that becomes a completely different talk. But the idea in accept-reject MCMC is that given any kth draw from the target, or kth draw from pi, we generate a theta star using some proxy proposal kernel Q, which gives us a theta star given my current step theta k. And now this theta star is taken as the next step theta sub k plus 1 with probability alpha. And this alpha probability is a function of the theta k where I was before, and it is a function of the proposal value that I've drawn. Now, if I don't accept it, then I reject it, which means that my next step is my previous step. So theta k plus 1 is equal to theta k. Now, this alpha is chosen in a particular way so that this whole process actually targets a right target distribution, or a correct posterior distribution. So you can't just choose any acceptance probability. It has to be a particular acceptance probability that guarantees pi invariance of the underlying Markov chain. If it is so that this alpha can be evaluated, so if we can actually calculate it and put in values of theta k and theta star, then step number 2 can be implemented. We can obtain an event of probability alpha, but by just drawing a uniform random variable u and checking whether u is less than or equal to alpha, alpha being this acceptance probability. So that's the standard method of drawing, of implementing something in step 2. That is based on the fact that we are assuming we are able to evaluate alpha. Now, there are the most popular acceptance probability alpha is the Metropolis-Hastings, or the MH acceptance probability. And what that does is you take your proposal kernel Q. This is the proposal that we use to draw my theta star. And so that's Q, and pi is my target density. So alpha MH, or Metropolis-Hastings, is minimum of 1 comma pi star divided by pi theta, and Q drawing theta given theta star and drawing theta star given theta. Now, of course, pi is unknown to us. At least the constant is not known, but the good thing is there's pi in the numerator and the denominator, so that unknown constant can get cancelled out. Pi tilde is potentially known to us, so we can write it in this form. This is the reason why Metropolis-Hastings is quite popular, is because the unknown normalizing constant, C, or whatever that constant is, that gets cancelled out. We know what pi tilde is, so we can just go ahead and implement this. Now, we can evaluate alpha MH easily if pi tilde is also known to us. So pi tilde being known to us, I'll just go back a slide or two. Pi tilde being known to us means this likelihood times prior is known to us. Okay. Now, there are cases where the likelihood times the prior is not known to us. And that can happen when I talk about intractable posteriors. We may be in a situation where pi tilde cannot be evaluated when my target distribution posterior pi is written in the form of integral eta g of theta comma eta given y d eta. As in, there is a nuisance parameter eta that needs to be integrated out, either because the prior is such that it is defined as a function of eta and eta has to be integrated out, or because the likelihood is such. And from Amir's talk, often in physics problems, we are faced with a likelihood that can't really be written down very cleanly. And so those are instances where pi tilde itself cannot actually be evaluated. Right? And particularly, the problem itself was motivated by Bayesian inference for diffusions, but we found plenty of other applications for these situations where the target density can't actually be evaluated anywhere. So here what happens is alpha MH can no longer be evaluated. So the step number 2, we can't really do with the knowledge that we've accumulated so far. Okay. So what can we do? So Barker in 1965, in mainly the physics and chemistry literature, proposed a different acceptance function. And that acceptance function was called Barker's acceptance function, which basically said instead of doing the min 1 comma the ratios, you can do something that's essentially a by a plus b, or pi times q divided by pi times q plus pi prime times q prime. Now, this also is a valid acceptance function. It also renders pi to be the target, the Markov chain to be pi invariant. But Barker's algorithm is not very popular. And the reason it's not very popular is due to the result by Peskun, who gave the following ordering. So Peskun's ordering result goes as follows, that if I consider a kernel, a Markov kernel, P sub B, which is the Barker's kernel, and P sub MH, which is the Metropolis-Hastings kernel, and if I take the Monte Carlo averages coming from the process generated by those kernels for any function, let's say H, then the limiting variance of those Monte Carlo averages, so limit n tending to infinity, n times variance of x bar for any of those kernels. So if I evaluate, or if I understand that for P sub MH and P sub B, then the limiting variance for MH is always bounded above by the limited variance for from the Barker's kernel. So this particular result, the result on the left-hand side, is one of the reasons why nobody really wants to use the Barker's implementation, because we can always do better with the Metropolis-Hastings implementation. But further, it was then next shown that actually one at least good thing is that it's not like the Barker's implementation is arbitrarily bad. It can be bounded above by 2 times the variance of the MH kernel plus a little bit of more variance coming from my target density. So this says that although Barker's is inefficient, statistically more inefficient, it is not so much so, or it is not too much so, because there is a reasonable upper bound available on that. All of that is to say that, of course, Barker's, if given a choice, we should use MH. But if for some reason we can't use MH, then Barker's is a reasonable thing to do because it doesn't have some weird unbounded variance in terms of the final performance of the Markov chain. However, so if I want to use, let's say, Barker's for this intractable posterior, it still doesn't help us because phi is still very much there. That means we still can't really evaluate alpha B. So why is Barker's going to be any more helpful than Metropolis-Hastings? Well, the reason is, and this comes, the third leg of the things in the title, which is the Bernoulli factory. What's going to help us actually implement an MCMC algorithm without needing to evaluate alpha is the use of what is called a Bernoulli factory. So let me segue into Bernoulli factories, and I'll come back to MCMC. So what is a Bernoulli factory? A Bernoulli factory is an algorithm that generates a Bernoulli event of some probability h sub p for some function h. H is any function that basically takes inputs as probabilities and outputs a probability. But this HP Bernoulli event is only generated using Bernoulli P events. So you can think of it as a machinery that takes in a bunch of Bernoulli events of some probabilities P and spits out a Bernoulli event of probability HP. Right? And it can take multiple inputs and give one output. Now what we want are events of probability alpha B to implement the second step of my algorithm, of my MCMC algorithm. But I want to return events of probability alpha B without evaluating alpha B because I can't evaluate alpha B. So in this particular paper, Goncalves et al., which is Goncalves, Latushinsky, and Roberts et al., they propose the following. They say, okay, let's take my numerator in the Barker's setup. So let's take my product, not just the numerator, but take pi times q, right? I evaluate it at either theta star or theta. So let's take my pi times q, evaluate it there, and let's assume I can find a c sub theta that bounds this pi times q. Okay. If I can do that, then I can write pi times q as c theta times some p theta, where p theta is nothing but pi times q divided by c theta. All of this is to construct something so that p theta is a probability, is a number between less than 1, and c theta is some constant. If I can do this, then what I want to do is basically generate events of probability c theta star p theta star divided by c theta star p theta star plus c theta p theta. This is what I want to do in terms of c and p. And what they do is they propose what is called a two-coin algorithm. So let's go over the two-coin algorithm. So they say, well, draw a first coin C1, which has probability of success c theta star divided by c theta plus c theta star. So this is a Bernoulli coin. Now, if this particular coin is 1, then you draw a second coin that is Bernoulli p theta star. Okay. If that is also 1, then you output 1. Now, the algorithm outputting 1 means that we can accept my proposed value, right? Because outputting 1 means alpha b, the realization of this step is 1, right? So go ahead and accept a proposed value. Now, if C2 is 0, then we don't reject it. We actually go back to step number 1. So at step number 2.3, we loop back to step number 1. Now, if the first coin was 0, then draw a second coin with probability of success p theta. Now, if that turns out to be 1, then you output 0. Outputting 0 means reject my proposed value and stay where you are. And if the second coin turns out to be 0, then you go back to step number 1. Okay. Now, it can be fairly easily shown that the above algorithm outputs 1 with probability alpha B, which is the Barker's acceptance probability. So if I take this algorithm and embed it into my second step of my accept reject MCMC, this gives me a Barker's MCMC algorithm. Now, the question though is, how do we actually sample Bernoulli p theta? So if I go back, p theta has pi q divided by c theta. C theta is some known bound. So p theta has pi in there, and I just said that I can't really evaluate pi, right? which means that drawing coins of Bernoulli P theta star or P theta is going to be challenging. So how do we do that? So to do that, we have to look at the particular form of pi. And if our pi is of the form presented before, then P theta is pi times q divided by c. Now pi is nothing but the integral with respect to g. Sorry, with respect to the nuisance parameter eta of some g. Now, although we don't need eta to be in a bounded space, but let's just assume it is, then I can actually estimate P theta unbiasedly by one simple Monte Carlo estimate. As in, I can draw a random variable n, which is uniform within the support of eta, and then set m sub theta to be q times g evaluated at that realization for eta, which is n, divided by c theta. If I take expectation of m theta with respect to my randomness coming from n, then this is just going to be integral over here, which is just going to give me p theta. Okay. Which means if C2 given m theta, if I draw a second coin, C2 given m theta as Bernoulli m theta, then probability that C2 is equal to 1 is the expectation of the indicator that C2 is equal to 1. Then I use iterated expectations and I condition on m theta. Now this inside expectation is p theta. And so now I just get p theta back. So the marginal distribution of the C2 coin is Bernoulli p theta once I condition on m theta. All of that is to say that to implement the steps here and here, I just need an unbiased estimate of p theta and p theta star. As long as I have that, I can implement steps 2.1 and 3.1, which is, and this is a particular way of getting that unbiased estimate. Okay, so I can take this methodology back into this algorithm, into the two-coin algorithm. The issue though in this algorithm is that at steps 2.3 and 3.3, this algorithm loops. Okay, so because it's looping, if my p theta or p theta star, either of these two are really, really small, it often goes to steps 2.3 and 3.3 and gets stuck in what could be an endless loop. Okay, and because of that, the MCMC is okay, but the Bernoulli factory is really, really slow. So the Bernoulli factory implementation can take a long time if either p theta or p theta star are really small. So this is really what was the main problem in implementing these algorithms, which is where our solution, quite a simple solution, comes in. What we notice is that we are in a situation where we can't really evaluate pi. So if we can't evaluate pi, the whole feature of Metropolis-Hastings and Barker's that the normalizing constant c cancels out, we don't need that feature anymore because as it is, we can't evaluate the acceptance probability. So the acceptance probability does not really need to be a ratio of the target densities only. We can open it up to even involve these normalizing constants that we don't know, as long as we can evaluate, as long as we can generate Bernoulli factory coins. So what we do is we propose a Portkey Barker's algorithm, where for some symmetric function d, alpha p or alpha Portkey is pi q divided by the same Barker's looking acceptance plus d in the denominator. Now d, we want d to be as small as possible because we don't really want to add too much to the denominator and reduce the acceptance. But d is something that's greater than equal to 0. And if d is symmetric, as in d theta comma theta star is equal to d theta star comma theta, then alpha p yields a pi invariant Markov chain, which means that as long as d is symmetric, this is a valid acceptance function. Okay. The particular d that we choose is 1 minus beta divided by beta, c theta star plus c theta. This beta is a function of the bounds that we've obtained. And this beta is some number greater than 0, between 0 and 1, actually. And if beta is equal to 1, this gets us back the Barker's algorithm, because beta is equal to 1, this whole thing goes away. Okay. So now my alpha beta, my Portkey Barker's acceptance function takes this form over here. And ideally, I want to choose beta very close to 1, so as to remain close to the Barker's algorithm. And that's because we obtain some understanding of the loss of efficiency based on Peskun's ordering for this particular algorithm. So for beta greater than 0, variance, the limiting variance from Barker's is bounded above by beta times the limiting variance from Portkey, plus some small variance quantity in addition to that. Now, this inequality is not really helpful to us, because what it's saying is that the Barker's variance is less than equal to beta times our Portkey variance, and that's not really the direction of the bound that we want particularly. The direction that we want is in the opposite direction, and so that's very challenging to do. But if in case p theta star and p theta are bounded away from 0 as a function of gamma, so p theta star and p theta are greater than both gamma, both are greater than gamma, then we can bound above our target, our limiting variance from Portkey as less than equal to a constant times Barker's. And this constant is the smallest when beta is equal to 1. And so that's really why we want beta to be as close to 1 as possible. But the question, though, is this just tells us that basically we are always going to be a little less efficient than my Barker's algorithm. So why do Portkeys at all? Why use Portkey at all if we're always going to be a little less efficient? And the reason is that even though statistically we'll be less efficient, our Bernoulli factory is going to be far more efficient. And so we actually arrive at a very efficient Bernoulli factory for this. So the Bernoulli factory goes as follows. It looks very similar to Two-coin, but it's called Portkey Two-coin. And the first step of this Portkey Two-coin is draw S from Bernoulli beta. And beta is this number that we want to be close to 1. That means more often than not, S is going to be 1, and sometimes it's going to be 0. Okay? So if S is 0, we output 0 immediately. Okay, so if S turns out to be 0, we say, okay, we reject this proposed value. Now, if S is 1, then we basically implement the original Two-coin algorithm, except the points where it loops, steps 3.2.3 and 3.3.3, it loops to our step number 1, which is drawing an S-coin Bernoulli beta. Okay, which means that if it loops, it actually has the opportunity to immediately reject my proposal with some positive probability that is chosen by us. So it basically allows us to immediately reject a bad proposal that would otherwise have us get stuck in very, very long loops, right? Which is really what happens in our original Two-coin algorithm. So basically, this random variable, Bernoulli random variable S, allows us to exit out of a bad situation at various points. And hence, if you were familiar with Harry Potter, Portkey is indeed a Harry Potter reference of being able to exit out of a situation. Okay, so hopefully the algorithm is making sense. The real key over here is that when it loops, it goes back to step number 1. When it goes back to step number 1, there is a positive probability, with the probability chosen by us, to exit out of an endless loop, an otherwise endless loop. Okay. Now, the other thing we note is that actually for both regular Barkers and our Portkey Barkers, we can also implement what is a flipped Portkey algorithm. So if we divide our Portkey Barkers by this product over here, pi times q at theta star and pi times q at theta, if we divide in the numerator and denominator, we just get something that looks like the same thing, but the inverse of each of those quantities, and a different symmetric function d prime, which means that I can now, instead of upper bounding pi and q, I can actually lower bound pi and q and get some c and p equivalently in terms of bounds. So if we can lower bound pi and q, we can implement a similar Portkey Two-coin algorithm, which we refer to as flipped Portkey. Okay, so let's just look at a particular implementation and an example of this whole sort of paradigm. So the example is that of a Bayesian correlation estimation model, where the idea is that given a certain amount of data, we want to estimate the correlation matrix of that data. Okay, so you can think of it as being really useful in stock prices, where there are multiple stocks are coming in, and we're trying to estimate how one stock is dependent on another, and trying to estimate the correlation structure of particular stock index. So suppose I have y1 up to yn given some r from a multivariate normal with mean zero vector and correlation matrix r. And so this r is a p by p correlation matrix, so these y's are p-dimensional each. And our goal is to estimate R via a Bayesian paradigm, okay? Which means I'll put a prior on R and possibly put priors on other hyperparameters in R. So a sort of popular model for this is, it was proposed by Lighty in 2009. So let SP plus denote the set of all valid P by P correlation matrices. Then we put the following priors on R. So on R, for each element Rij inside R, basically you put a restricted Gaussian prior with mean mu and variance sigma square, where the restriction is such that the final matrix R needs to be in the set of a valid correlation matrix. Otherwise, the model is not going to be correctly described. And so because of that restriction, we have this constant outside, this L mu comma sigma squared, that is basically an integral over that restricted space that allows it to integrate to 1, allows the final density to integrate to 1. Now further, because mu and sigma squared are going to be parameters of interest as well, we put priors, or Lighty put priors on those as well. So that mu has a Gaussian prior, means zero variance tau square, and there's an inverse gamma prior on sigma squared. Okay, and tau A naught P naught are hyperparameters. So now the interest is in the posterior distribution of R, mu, and sigma squared. Okay, so for this, what we can see is that for this, that the joint posterior distribution of R, mu, and sigma squared is going to have L mu sigma squared in there in the form of this inverse integral, which we cannot really evaluate because this SP plus is a very complex space to integrate over. Right? So let L, this is a small L, let L be equal to P times P minus 1 by 2. Those are the number of unique elements in an P by P correlation matrix. And so the MCMC algorithm is to implement a component-wise algorithm where each element of the R by R correlation matrix is updated via its what is called a full conditional. So conditioning on every other parameter and the data. So that is proportional to R determinant of R to the power n minus 2 times this quantity over here, with the restriction that R is less than and greater than some bounds. Now this can be implemented using a sort of straight Gaussian proposal Metropolis-Hastings update, because this doesn't have any unknown constants. Okay? This has no L's floating in it. However, for the updates for mu and sigma squared, to update mu and sigma squared to draw from their conditional updates, these are proportional to L mu sigma squared times something. And this L is an integral. So it's an inverse integral, which means that we can't really evaluate this density at all. Right? So in the original paper, in the original works, they proposed what is an approximate shadow prior that approximates that targets an approximation of our true posterior distribution. So instead of going into those approximations that we can't really quantify, we can actually implement an exact MCMC algorithm via Bernoulli factories. So let's just look at the update for mu. So if we focus on the update for mu, mu is f of mu given R and sigma squared is proportional to L. This is the inverse integral times what's inside the integral. Now L inverse is equal to this integral over here. Now, because L inverse is equal to this integral, it's much easier to lower bound f rather than upper bound f. So we're going to implement the flipped Portkey Barker's algorithm. Okay. And in this particular case, what we note is that the integral is over the space of all P by P correlation matrices. Right? Now, this is a restricted space, but we can always upper bound L inverse by the idea that each of the Rij's are between -1 and 1. And that's because these are Rij's are correlations. So Rij's have to be between -1 and 1. So we can actually upper bound L inverse by an integral over a -1 to 1 p-dimensional cuboid, which gives us an upper bound, which gives us a lower bound on F mu. So L inverse is upper bounded by this quantity here. That's just coming from upper bounding it on a cuboid from -1 to 1. And that becomes my C tilde sub mu. And this gives me a lower bound for F mu. So lower bound for the full conditional. So for this full conditional step, we can implement a flipped Portkey algorithm. Okay. So let's actually, we'll now look at the performance of the algorithm itself. We actually study the closing prices of 4 major European stocks from 91 to 98. So that's the data coming in. P is 4-dimensional, and our actual data are from 91 to 98. So the first plot I show you is the log of the number of loops for mu for the Bernoulli factory. So every time the Bernoulli factory loops, I add an index for basically every time it loops for one particular step of the algorithm. So I run my Markov chain, both my Markov chains for length 100,000, so 1E5, and I run with beta equals to 1, which implements the original Barker's algorithm, and I implement with beta equals to 0.9, which is the Portkey algorithm. And in gray are the number of loops for Barker's, or the Two-coin, and in red are the number of loops for Portkey. Now, what the Two-coin algorithm does is basically you see a cluster happening over here where it often goes beyond e to the power 8 number of loops. So over here, it's going into e to the power 12 number of loops, which is on the order of millions. So to do one Markov chain update, it's having to do 1 million loops before it actually figures out whether it wants to accept or reject. Versus the Portkey, which because of the Portkey coin has basically a cap, a probabilistic cap at around e to the power 4, right? So it doesn't ever basically go beyond e to the power 4 in this particular implementation. Okay, which is great. So that means that because of that Portkey coin, it's basically rejecting bad proposals. But are we sure that the efficiency is similar? So let's take a look at that. I can also look at ACF plots, or autocorrelation function plots, for both mu and sigma square, which are the two updates which were intractable for us. And for beta equals 0.9 and beta equals 1, they're statistically similar to each other. I mean, whatever visual difference we see is potentially just estimation difference. Of course, theoretically speaking, the Portkey algorithm is going to be a little less efficient. And over here, it's only marginally so, if at all. Right? So we get essentially similar performance in terms of efficiency, but we get massive gains in waiting times. So let's look at another sort of analysis of what the waiting times look like. So what I show over here are average results from 10 replications of length 1E4 or of length 10,000. I present for two values of beta, again, 1, which is Barker's, and 0.9, which is Portkey. I present effective sample size, which is a way of measuring how many independent samples I have from this algorithm. So Markov chain Monte Carlo gives us correlated samples. And so what I want to know is essentially how many independent samples do these correlated samples correspond to? And so the larger the number, the better it is. So Barker's gives us 542 from 10,000, and Portkey gives us 496. So slightly smaller, definitely slightly smaller. However, if I look at ESS per second of implementation, Portkey does significantly better. But that's really not what is the main utilizing feature. If I look at the max number of loops, so this is basically over 10 replications, what is the mean of the max number of loops for mu? Sigma square is very efficient, but mu, I see about 2 million, about 2 million loops is the average maximum for Barker's, and 34 is the average maximum for Portkey. Now, what happens basically in this implementation is one particular implementation may run fine, but another one may ask you to wait for 15 minutes. And it's that uncertainty of when my simulation is going to stop that is incredibly frustrating with the two-coin algorithm, versus the Portkey, which almost gives you a high probability event that it's going to finish in a reasonable amount of time. Now, we could only do 10 replications with beta equals to 1 because this would often get stuck in very large loops. And sometimes it wouldn't, and sometimes it would. So, of course, in any sort of Monte Carlo replicated study, we'd want to do a larger number of replications, but that was very, very difficult when comparing to the two-coin algorithm. What was also very, very difficult was actually utilizing a good proposal queue. A good proposal queue can be found by the works of Sanket Agrawal, who worked with me before moving on to Warwick as a PhD student. So we came up with what is an optimal proposal for Barkers. And when we implement that optimal proposal for Barkers, what happens is that for beta equals to 0.9, so for the Portkey, it gives me 10,000 samples in 40 seconds with an ESS of 514, which means it's giving me reasonably good samples and very quickly. But because it's an optimal proposal, it's actually trying to reach farther and farther away. And the farther it tries to reach, the more difficult the original two-coin Bernoulli factory becomes. Which means that for beta equals to 1, I implemented one thing and I could barely get 1,000 samples in 24 hours. And it was just stuck in one particular loop for about 24 hours. And at which point we had to forcibly stop the simulation. It is this particular uncertainty which limits the original Barker's algorithm, the original two-coin algorithm, to actually explore the state space sufficiently enough for my MCMC algorithm. Okay, so in conclusion, so the work itself is actually now available online and at Biometrica. But really the advantages of the Portkey and in general the Bernoulli factory spaces is that for our Portkey implementation, the actual Markovian dynamics are only mildly altered if I choose beta equals to 1 or very close to 1. So I get almost the similar amount of efficiency, but in addition, I get an exact MCMC algorithm, which is really different from a lot of the other algorithms that are implemented for intractable target densities. And it turns out that the Portkey implementation is significantly more robust because we're not really staring at a blinking cursor for an arbitrary amount of time. We have an understanding of when we'll hear back from the algorithm. Now, there are disadvantages. For example, there's certainly a loss of efficiency. For different values of beta, we can get arbitrarily bad mixing of the Markov chain. And of course, this is assuming we can actually find the bounds C theta or the upper or lower bounds. In some implementations or applications, we weren't able to actually get good bounds for this algorithm to work. So that's probably the most highlightable disadvantage. If there's time for questions, I'd be happy to take some. Thank you for being a good audience, an attentive audience. Thanks.